Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today what I want to do in this video is to talk about vector bundles and give you a first definition of what they are. Once we have a simple definition for what they are, we can actually use them to define invariants. For example, we can look at the tangent bundle and see how it is in some sense an invariant for topological spaces which arise as manifolds. Okay, so the theory of vector bundles you can do in various geometric categories. Okay, so what we'll do is we'll fix C a geometric category, and basically the ones that we're interested in are topological spaces, or real manifolds, or complex manifolds. And sometimes in these three cases, to distinguish what setting we work in, we use different words. For example, we can talk about just topological vector bundles, or smooth vector bundles in the real manifold case, or holomorphic vector bundles in the complex manifold case. Okay, so to do that definition, just let me remind you briefly how informally you should think of a vector bundle. So basically, this is just a family of vector spaces which varies continuously over some topological space or real manifold or some complex manifold. Okay, so before giving the definition, I need to talk about morphisms over an object. Okay, so that's encoded in this little lemma definition that we'll need. So the types of objects we'll want to look at are actually morphisms in our category. So let's just pick one. Say, for example, the morphism P from V to U. Okay, so maybe it's defined like this. Here's our V, and it maps down to U like this. Okay, so why are we interested in such a morphism? How do we want to think of something like that? Well, the way we want to think of it is as follows. So for each point down here inside our U, maybe X here, we can look at its inverse image inside here. So maybe this is a map which is like projection down, in which case maybe this is its inverse image up there. So this here will be the inverse image. Okay, so that's P inverse of X, this thing here. Okay, so as you vary this X, you'll get a different inverse image. So one way you can think of this morphism now is it's these inverse images, and they vary one for each point of this, what we call the codomain space, like the base here. Okay, so we want to think of this as a family of geometric objects that varies as you vary the point along this U here, this codomain. Okay, and now what we want to do is, suppose we're given two of these objects. Okay, so map P from V to U and map Q from W to U. Okay, so maybe here's V to U and W to U. And we want to talk about what's a U morphism. Okay, a morphism from V to W which respects these two maps. Okay, so let's quickly define what a U morphism is. Okay, it's just a morphism from V to W such that the following diagram commutes. Okay, so here you've got maps from V to U, W to U, they're given by P and Q, and you want another morphism inside your category, phi from V to W, so that this commutes, which we write like this, and what that just means is that the map from V to U is the same as the composition of the map V to W and W to U. Okay, so that's what it means by commutes. So to write that more formally, what that means is that this map P, so that is P is equal to the composite of, you do phi first, and then this Q. Okay, so in this case we say the diagram commutes. Okay, so let's try to think of it in terms of how I want to view this morphism. Remember, I want to view this morphism as just a family of objects or sub-objects of this V, which varies as I vary this point along U. Okay, so above X, I have this P inverse of X, and inside this space W, I have Q inverse of X. So let me put in Q inverse of X. And so what does it mean that this diagram commutes? What does it tell us about these two inverse images? Well, this is what we have. in this case, for any point x inside our codomain U, that we'll call the base of this morphism, phi actually maps this inverse image, P inverse of x, to Q inverse of x. Okay, so this P inverse x we also sometimes call the fiber above x. Okay, the fiber above x this time inside this V, and Q inverse x, the fiber above x inside W. So it maps this fiber to this fiber here. And the reason for that is actually very easy to see why that's true. Okay, so let's suppose you have a point inside here in this fiber, and you want to see, well, does phi map it over to here if we assume that this phi is a U morphism? Okay, so how do we check that a point here does indeed get mapped to a point here? Well, to be inside here, remember this is just the inverse image of x, so you just have to show that the map of that point down to here is indeed x. But to go around this way is the same as to go around this way, and the image of this point inside here is indeed x, since it's in the fiber above x. Okay, so very easily we see that if phi is a U morphism, it sends this inverse image, this fiber, to the corresponding fiber inside W. Okay, so in fact it's quite easy to see that, at least theoretically, if instead of we were working not inside C, which is one of these geometric categories, but inside the category of sets, to be a U morphism means precisely this condition here. It sends fibers to corresponding fibers. Okay, so that's the way we want to think of a U morphism, and that's going to be important for us when we come to define a vector bundle. Okay, so it's basically one that sends corresponding fibers inside V to corresponding fibers inside W. Okay, so that's the most important feature that we have for these U morphisms, and it's now fairly easy to define what it means to be a U isomorphism. And a U isomorphism is just a case where you have a U morphism, like this one here, so this diagram commutes, where this phi is also an isomorphism. So other terminology that you'll see, which is fairly common, is instead of U morphism, sometimes you say phi is a morphism over U. Okay, so often we write it like this, so it sits above the U. And this is also sometimes said to be a U isomorphism, we say is an isomorphism over U. So we can now give our definition of a vector bundle. So just as for vector spaces, you have to pick a field. In this case, we need a field as well. And the most important fields for us will be the reals or the complex numbers. And the important thing that we'll need is that these two should also be objects in our geometric category. So for example, if you're working with real manifolds, both R and C, they do give you geometric objects because they're both real manifolds. And for C, this is also a complex manifold. So in that case, you can use C. Okay, so what is a rank R vector bundle on an object X inside our geometric category C? Okay, so remember the informal definition was a family of vector spaces of dimension R. Okay, so to get that family, what we'll do is we'll consider a morphism, P from V to X. Okay, so what were the members of that family? Well, for each element little x inside this X here, we look at the inverse image. So what we want to do is, looking at all these inverse images, we want to say that that is an R-dimensional vector space over F. Okay, so there's quite a few things that's going on in this hypothesis here. Firstly, this is part of the data. For each of these fibers, P inverse X, you have to make sure that you put the structure of a vector space over F, and that vector space has dimension R. So that's the first thing to note. The second thing to note is that P inverse X, well, what is that type of object? Okay, so what you want firstly is that this should be an object inside our geometric category C. Okay, so either a topological space or a real manifold, or complex manifold, whichever category we worked in, it has to be of that form. Then you also want the fact that an R-dimensional F space is also in that category. So basically you want to say that they're isomorphic, okay? So you give some sort of structure on this object of C, and that structure is the additional structure of a vector space over F. Okay, so that's the first part. That gives you, so to speak, just a family of vector spaces of dimension R over X. But of course you want this to vary nicely. You don't want these vector spaces to jump around in some discontinuous function, but in some continuous or sometimes a smooth or holomorphic fashion. And the way we'll do that is we'll introduce the following local triviality condition. So this is the second important condition that we need to define a vector bundle. Okay, so how do we define this local triviality? We do it as follows. So we look at each point inside the bottom, each little x inside big X, and we insist that there exists some open neighborhood U of this point X, of the base, such that basically this vector bundle just looks like the trivial bundle on this open neighborhood. Okay, that's a bit of a mouthful, so let's see what's going on. So remember here you've got a map from V to X, so you can restrict it so you're just looking above U. Okay, so you just look above U, and then above U you're going from P inverse of U. So you restrict P to P inverse U maps to U. Okay, so on this U you can also consider the trivial vector bundle, which is just U cross F to the R. Okay, so what is this? So this will be a morphism to U, and the morphism is quite simple. This pair U comma V you just send to U. Okay, so this is indeed a family of vector spaces over F. Okay, so for each U you can fix that U and you let this V vary across this FR. So it's just a copy of FR. Okay, so you have two maps to U, and then we can talk about a U isomorphism from here to here. So this local triviality insists that you have this U isomorphism and actually a little bit more. And what's that little bit more? So remember, when you have a U morphism, that means the fibers inside here get sent to the fibers inside here. So let's have a look at the fibers in these two places. Well, the fiber above any U here is just a copy of this FR. So that's an FR here. Okay, and the fiber above that U inside here, P inverse U, what did we say? Well, that's also some R-dimensional vector space over F. Okay, so the two fibers on the two sides, they'll be R-dimensional vector spaces over F. So we can insist, not only do we have an isomorphism in our category C, so in other words, a homeomorphism if we're looking at topological spaces, or a diffeomorphism if we're looking in the case of smooth manifolds and so on, but these two both have vector space structures, so we can ask that this is an isomorphism of vector spaces as well. And if this condition holds, then the local triviality condition holds, and we get a vector bundle. And this is a vector bundle of rank R. Okay, so there's quite a bit going on in this definition, and it's good to have a look at a simple example. So we'll look at the following simple example, which is very important in mathematics and in geometry, and that's the following. We'll look at a real manifold, smooth manifold, we'll call it X, and in this case, well, R is also a real manifold. Okay, so we can look at F equals R, and the vector bundle I want to give you is going to be V. So let's suppose this V is going to be what is called the tangent bundle. So what is the tangent bundle? So let me give you the definition. I'll use a definition which is perhaps a little bit loose, but nevertheless captures the feel for what the tangent bundle should be. Okay, so Tx is going to be sets of pairs. So firstly, you have a point inside our manifold X, and then the second element in the pair is going to be a vector inside the tangent space to X at this little x. Okay, so it's going to be the set of all these pairs. So this will make complete sense if we look at embedded manifolds. So just look at a particular example here, okay? So here perhaps we have something like a sphere or spherical type of object that sits inside R3. Okay, it's a manifold, so to be a manifold basically means that locally it looks like Euclidean space. So in the neighborhood of any point like this x here, right, you can find some neighborhood like that, so U, and it looks like some open subset of R2 in this case for this sphere. Okay, so what is this? So basically you're living inside some Euclidean space if you have an embedded manifold. So you have a pair of a point inside the x, okay, and then you can look at the tangent space. So here if you have the sphere you have a tangent plane, okay, and so you have a vector which goes from the point of tangency and sticks out in that tangent space, okay. So that'll be your second element inside here, okay. So I claim that this actually gives you a vector bundle on my smooth manifold X. And so how does that work? So what was the data that we need to give a vector bundle? So remember, it should be a family of vector spaces. So to get this family, we need a map from this vector bundle V to X. We need to put a vector space structure on each of these fibers, and then we need to check this local triviality condition. So let's do those three things. Okay, so what's the map from this tangent bundle Tx to X? Well, I hope it's fairly easy. All we do is we forget about this tangent vector V. So we just map X comma V to X. Okay, well, what's the inverse image of this X? We need to give that a vector space structure, okay? So in this case, P inverse X is just this tangent space. So the dimension of this tangent space, of course, will be the same as the dimension of the manifold. Okay, so that will have constant dimension as you vary X. So this gives you a vector space structure. Okay, so if you're not familiar with manifold theory, if you go back to our sphere, let's see how that works. So remember, in the case of the sphere, at any point you can look at a tangent plane. So that's a plane, so usually planes are not vector spaces. But since you have a distinguished point on that plane, okay, that's the point of tangency, you can make that the 0, and changing coordinates by translating to make that the 0 means that that plane you can shift down to a two-dimensional subspace of, in this case, R3. Okay, so this is indeed a vector space, and the dimension will be constant as you vary X equal to the dimension of that manifold. Okay, so we've done the first two things I mentioned here. We've got the morphism, we've got a vector space structure on each of the fibers, and we now just have to check the local triviality to see that it is indeed a vector bundle. So let's do that now. Okay, so remember, being a manifold, what does that tell you? That means that in the neighborhood of each point X, it looks locally like Euclidean space. Okay, so you can find for each X some open neighborhood U, and it looks like some open subset of Euclidean space. Okay, so an open subset W of R to the N, and this N here will be the dimension of the manifold. So let's suppose that the coordinates on this R to the N, this Euclidean space, are x1 up to xn. Okay, so now at any point of Rn, you have a basis for the tangent space. Okay, so what is that basis? Well, the basis is just given by the, so to speak, the d dxi. Okay, so they're in the directions of the coordinate axes. Okay, so they're the d dxi. So you can look at the direct sum of that, and that generates the tangent space to any point here. So if you look at P inverse of this open neighborhood of this X, okay, since this U is just like this W, and the way manifold theory is set up, of course, is that this P inverse U, that's the tangent bundle, so to speak, over U. That looks just like the tangent bundle over W, because this U is diffeomorphic to the W. So this is just basically the tangent bundle to W, and of course the tangent bundle to W is just W cross this vector space here, this n-dimensional vector space. So this is trivial, okay? And hence this is trivial as well, okay? So we have this local triviality condition holding. Now that we have the definition of a vector bundle, the next natural thing, of course, to do is to define what are morphisms of vector bundles. And then, of course, what are isomorphisms of vector bundles? Well, that's quite easy to do, and let me do that right here now. So suppose now you have two vector bundles, P1 from V1 to X and P2 from V2 to X. So the notion of a morphism that I'll look at here is called a strict morphism. So what's a strict morphism of vector bundles from this one to this one? So this is an X morphism, so both of these are maps to X, so you can talk about an X morphism from V1 to V1, V1 to V2 rather. So phi is an X morphism from V1 to V2, and hence, remember, that means that it sends fibers to fibers. So let's have a look at all the fibers. So for each little x inside big X, you get a map from P1 inverse of X to P2 inverse of X. And remember, these two are vector spaces since these are vector bundles, okay? So they may have different rank, okay? So that's fine. We can talk about morphisms between vector bundles of different rank. But in any case, these are vector spaces over the same field. And the extra condition that we require is that these maps are linear maps of vector spaces, and also, once they're linear maps, we can look at the rank, and we insist that the rank of this phi x map is going to be constant as you vary this point x over this base x, okay? So basically, it's a family of linear maps from this vector space to this vector space, and we throw in this extra constancy of the rank condition here. And once we have this definition of a strict morphism, it's of course very easy to see what is the definition of an isomorphism of vector bundles. Here, you just want this X morphism phi from V1 to V2 to be an isomorphism. Okay, so once we have the notion of isomorphism and morphisms of vector bundles, we can actually use them to get invariants. So these vector bundles in some sense give us invariants, and that's what I want to show you in this next example here. Okay, so X here is going to be a Lie group, and we're going to work in the setting of smooth manifolds. Okay, so if you don't know what a Lie group is, let me say roughly what it is. Okay, it's essentially a manifold, which also is a group where the group structure respects the manifold structure. In other words, multiplication is a smooth map and the inverse is a smooth map. Okay, so the simplest example to keep in mind, that's the one that you should think about when I go through this little argument here, is the following. We can look at the circle. Okay, so that's certainly a one-dimensional manifold, and it also has a group structure. Okay, so why is that? The easiest way to see the group structure is as follows. Okay, so this circle S1, you can think of it as just the real numbers modulo the integers. Okay, so the real numbers modulo the integers, that's certainly topologically a circle. But what you find here is that this set of integers is a subgroup of the group of real numbers. So of course this is also a group as well. Okay, so you have a group structure on this that's induced from the group structure on R. So that's a Lie group. Okay, so here you have a Lie group. And one fact that you have is that the tangent bundle to a Lie group G, so TG, is actually trivial. Okay, so this is a wonderful fact about Lie groups. Okay, so in other words, if you have a manifold with this extra nice group structure on it, then it tells you something about its tangent bundle. Okay, it has to be trivial in the sense that it's just G cross some vector space. Okay, so let me show you why that's true, because it's quite easy to see as well. So in this case, what is that vector space? Okay, so the way I'll prove this is I'll show you that this tangent bundle TG is actually isomorphic to G cross, and the vector space is just the tangent space to G at the identity. Okay, so if you're getting a bit lost, let's go back to this simple example of the circle here. And let's see, what is the tangent space to the identity? So suppose the identity is here. What is the tangent space here? So it's just the tangent line. Okay, so there's the tangent space to G at the identity. And of course, to think of it as a vector space, you make this point the 0 here, okay? So it's a one-dimensional vector space in this example. And now I need to give an isomorphism from here to here. So how do I do that? Okay, so I do it as follows, okay? So suppose you have an element of this trivial vector bundle, G cross T1G, okay? So you've got a point here, G here, and you've got a vector in this tangent space. Maybe that V there. Well, the key point is the following. We have to use the group structure. And how are we going to use the group structure? Okay, so the point is that you can multiply on this group by G. And that will send the elements of the group back to itself. Okay, so there's an automorphism of this group, the manifold structure of this group, given by just multiplication by any group element. So we fix that group element G and we just do that, okay? And the key thing is that actually that maps the tangent spaces over as well. So what happens, so basically what is this multiplication by G on this circle? Well, basically you just rotate by G, okay? So that's all it does. Okay, you just rotate, so this 1 goes to G. Okay, that's how the group structure works here. Okay, so what happens when you rotate? Well, you send this tangent space to G at 1 here, you rotate it all the way to the tangent space to big G at this little g. Okay? So this automorphism of the manifold structure of G will send this tangent space to this tangent space. So this vector gets to some vector over here. And that's basically the image of V under dg. That's in differential geometry notation here, okay? So it's dg of V. Okay? Now, of course, here what you have a pair consisting of a point on the manifold and a vector in the tangent space at that point. G comma dg of V is just a point of the tangent bundle. Okay? And so you see here that quite easily that this will actually give you an isomorphism. So it's going to satisfy all the things here. Okay? So you certainly get an isomorphism. And the other thing is that on each of the fibers, you'll have an isomorphism of the one-dimensional vector spaces involved. So basically, here, the fiber over any point is going to be just this T1G, so this tangent space at 1. And over here, it's going to be this tangent space here. And all you've done is you've identified using this DG map, okay? So this multiplication by G induces an isomorphism of this vector space, which is the fiber over here, with this vector space, which is the fiber over here. Okay? So of course, this is rather neat. If you look at this picture, you see, it's actually not clear, just looking at the tangent bundle, even of a circle, that the vector bundle is trivial. Okay? That it's isomorphic to the base x across some vector space. So this is a rather interesting fact, okay? And it becomes even more interesting as you make the group more complicated. Okay, so let's just see how, in fact, that shows that now that we have a notion for isomorphisms of vector bundles, we can use the tangent bundle as an invariant for a topological space, okay? So my first remark here is that the key thing is that you have a group structure which allows you to do this argument, perform this argument here, okay? So that's really nice, okay? So in particular, if you're Lie group is what's called a complex Lie group, okay? So instead of looking at real smooth manifolds, you can look at complex manifolds, okay? And suppose your multiplication now is holomorphic, as is in the inverse, then you get a complex Lie group. And the same thing applies. You can look at the holomorphic tangent bundle, and you will get triviality of that holomorphic tangent bundle in this case, okay? So that tells you some things, okay? So suppose you want to study one-dimensional complex manifolds, and suppose you're given one X, okay? So one really nice set of one-dimensional complex manifolds that you can find out about in my video on complex analysis and algebraic geometry are the elliptic curves. They're of the form, so the base one-dimensional complex manifold you have is C, but you can quotient out by a discrete lattice that's isomorphic to 2 copies of Z as a group, and that will give you a one-dimensional complex manifold. And you can ask, well, if you're given some X which is a one-dimensional complex manifold, is it of this form? And that's a good question. And the thing is that now we have a way of finding out, because this has a group structure, because this lambda is a subgroup of C. Okay, so since it's a subgroup of C, this has a group structure. So that means its tangent bundle has to be trivial. So one way to test if this X is isomorphic to an elliptic curve, in other words, some C mod lambda, is to check that its tangent bundle is not trivial. Okay, so that's a wonderful way of doing it. And in fact, the converse result holds too. Given some one-dimensional complex manifold, if it's compact, then it turns out that if it does happen to be trivial, then it will be an elliptic curve. So this is a precise criterion, a necessary and sufficient criterion for checking whether something is or is not isomorphic to an elliptic curve. And this is one of the reasons why it's important to study vector bundles in geometry. I hope you enjoyed this adventure in pure mathematics.